Hello, everybody. It's my pleasure and honor to introduce Yarom Baram as today's speaker in the virtual Informal Systems Seminar. Yarom's an old friend of mine from Cambridge, Massachusetts days, and I'll read a brief version of his biography because you're much more interested in hearing from him than from me filtering or distilling his distinguished career. So I'll keep it short as I can. So Yarom Baram is in the computer science department at the Technion Israel Institute of Technology. He received his bachelor's degree in aeronautical engineering from the Technion in '72, master's in aeronautics and astronautics from MIT in '74, and the PhD degree in electrical engineering and computer science from MIT in '76, which was the time I met him. So in the '80s, he was mainly interested in theoretical issues of control systems, information, and then, as he says, an incidental acquaintance with movement impairments of patients with Parkinson's disease led him to the development of closed-loop virtual reality device for gait entrainment, which I think we're going to hear about today. Received a US patent in 2004. As he, I'm sure, will explain, the device has proved highly effective for gait improvement in a variety of other neurological disorders, which I won't list. So he's the author of The Subcritical Brain, which appeared in 2021, and Motion Control, also published by World Scientific, which is coming out very soon. So with no further ado, there they are on the screen. And so with no further ado, I'll hand over to Yarom.
Thank you, Peter. I couldn't do it better. All right, my interest in, say, memory, cognition, and motion control have brought me to write two books in recent years. One was The Subcritical Brain, which appeared in 2021. And that was in mathematical neuroscience. And the other book, which is about to appear this month in the same World Scientific House, is about motion theory, which, as Peter mentioned, was my first interest and career. And in this book, it's about 2/3 of the book, and it's completely mathematical. So I will not really spend too much time on that, but more on medical support, which, as Peter mentioned, became a major interest of mine. First, I should also thank Peter and for inviting me. So I took a mathematical look at things here, and I was guided by the main idea to investigate what may be the most relevant mathematical approach to the experimental neuroscientific and medical processes involved, which meant that I was looking at the mathematics and then made sure that it's relevant by asking and trying to make sure that the neuroscientific equation, the neuroscientific explanations and achievements are in step with the mathematics. So that's just my point of view. The first part I call neural connectivity linguistics. And to me, it's the first driver of the mind. Why? Neurons are letters. Connected neurons or neural circuits are words. Connected neural circuits are sentences. And something a bit more complex, but you'll understand it later on, is that connected primal size neural circuits or primal size neural circuit trees are structured languages. So we'll sort of understand this later. About neural connectivity, neural membrane is active if its potential is above minus 60 millivolts and silent if it's below minus 69 millivolts. That was a discovery made by a Russian neuroscientist, Melnik, in 1994. 5 years later, 2 American neuroscientists extended this result to synapses being active or silent according to the same numbers. Now me, for mathematical simplicity, the corresponding polarity is active or silence, which is described above. I used just 2 numbers, 1 or 0. If it's active, it's 1, and if it's 0, if it's silent, it's 0. Here's a neuron, and it's actually a neural circuit of a single neuron circuit. It has the neuron is a circle, and the axon and the back synapse complete a circuit, a complete circuit. Now what should I call it? The 0-1 aspects are produced by the gates that you see here. Okay, so the gate can be open or closed, and that would produce 3 types of neuron circuits. As you see, one has both gates closed. The other one has only one gate closed. The one that's open doesn't play any role. And then there's a silent neuron without any gate open. So you might say, okay, a silent neuron doesn't count, doesn't have any role. But that would be a big mistake on your part, because in 2014, a Nobel Prize for physiology and medicine was given for the discovery of the role of the silent neuron. They called it role in positioning, and I'll get into this, how this affected without even knowing about it. Then it affected my approach to things. If you go into bigger circuits of 2 neurons and more, then you have many permutations of the gates. And for instance, 2 neuron circuits can have 21 word code, if you count all the permutations here. And okay, neural circuits are very similar to random graphs. That's something else I paid attention to in recent years. Random graphs were presented mathematically by Erdos and Reni, two well, okay, it's European, let's say, let's make it simple. Mathematicians, they said that given n neurons, and they spoke about nodes of a graph, if the connectivity probability P between pairs and pairs of nodes, or in my case, neurons, if it satisfies the subcriticality condition, P equals C over N, where N is the number of neurons or nodes in their case, and C is a number between, any number between 0 and 1. In this case, an upper bound on the size of any connected neural circuit, which we call a word, is of order log n. This is an amazing discovery because log n is very small. And it tells you that in this case, in the case of low probability of connectivity, you are down to very small circuits. And for instance, in the brain, there are 10 to the 11 neurons about. And there are at most 4 times 10 to the 9 words. The reason being that log of 10 to the 11 is 25. I should have said the circuits could not have more than 25 neurons per circuit. So you see that the number is tremendously smaller compared to 10 to the 11. Someone else came up with the idea of a supercritical neural circuit. That was Bulobas in his article in 2001. And I can almost skip this, but you get to, for one thing, it allows for what he called the giant component, which would be a circuit of n to the 2 over 3 size. But the other circuit would still be of order log n. But of course, if P gets bigger, then the number of connected circuits will be smaller. For instance, if P is 1, then the number of neural circuits is 1, right? Everything is connected, the whole brain is connected, and you have 1 circuit. So what good is it for? It makes no sense. Staying with the subcritical approach made sense to me, and that's why I call it the subcritical brain. And here I say, what is better, subcritical or supercritical? So I've already given you the answer, and you could figure it out from natural languages. We know that in natural languages, the words are very small. In English, there are about 200,000 words in use. I've seen the claim to millions, but let's stay in this number. Then an English word is on average 4.7 letters big, small letters. Of course, large circuits, as I sort of indicated before, limit the information capacity of the brain. So in my more intuitive thinking about this is that hearing and speaking and memorizing things must have an echo in the mind, right? Because we say words, we understand words, we speak words. So there must be something in the brain that is able to create those words. And you need to have a sort of at least a circuit, a neural circuit for a word, which is why I think that such small words make sense in many ways. Let's say something about Hebbian connectivity. Hebb, of course, was a Canadian scientist. In 1949, he published a book, The Organization of Behavior. Hebbian theory explains how neurons might connect themselves to each other. And if we have a column of n neurons, say, whose axonal polarity states, which, as I said before, is a 0 or 1, and you have n neurons, you take the value 1 with probability p. Suppose that there are m, some number of such random columns, and these are the W's are the axonal state 0 or 1, and you produce a matrix. That's a Hebbian approach. You produce a matrix of W of the column W times W transposed outer product. You get a matrix. Here is a W, and W actually tells you how neurons are connected. And what you see in the subcritical case, in which I chose a number of neurons to be 10, P to be subcritical 0.5 divided by n. We said anything between 0 and 1, okay, divided by n. And m is 10, the number of columns that you can have. And you come up with a set of neural circuits with 4 single neurons and 1 double neuron circuit. So you have altogether five circuits. If you go to subcritical, you see that, okay, with the same 10 neurons, and the same number of columns, but a supercritical value for P, 1.5 over n. You go to the Bolobas answer, 10 to the 2 over 3, you end up with 4.6 neurons in a circuit. And it doesn't satisfy the limit of log n. And you end up with three circuits. Now, as we said, when you have large circuits, you don't get anything in capacity. Quite the contrary. So before I had 5 circuits, 5 words, and here I have just 3 words. So again, the win of the subcritical approach. Let me say something about, I think I was here, right? Was I here? Sorry, wasn't I here? I believe I was. Yeah, okay.
There.
All right. let me tell you about the magical number 7. That was another subject I came across, and it turned out that a psychologist by the name of Miller has published a paper in 1956, which he called the magical number 7 plus or minus 2. Now, this paper is known as having by far the most highly cited number of publications in the psychological literature. What Miller did was tested patients by certain phenomena applying either muscular tunes or electric skin stimulation, punching the screen in different places, or playing a visual, showing or marking a visual dot location, like on a board. And the patient, the examined person has to memorize, say, the places of the dots or the musical tunes that were played or the electrical punches he got. And it turns out, and that's what the Miller paper was about, that a person that can't remember more than 7 items. Now, I call these particular items categories because there are points, 7 of them, in the same category, or punches, same category, or musical tunes, another category. So what is magical about the number 7? Miller didn't do any mathematics, but I picked it from here and I said, okay, if I have 2 neurons in a circuit, I can arrange the circuits I showed you before in 4 columns of 7 circuits each. And the circuits here form categories because they're very similar. They differ in something small from each other. But why can't you go beyond the 7? Because what you get is repetitions, okay? And as far as memory is concerned, once you've memorized and expressed the 7 items in a category, going beyond doesn't buy you anything. But we know that we know that well, let me take one short point here. If I took the groups of circuits I showed you in a minute before the slide before, and I run the firing rates of the 4 categories, what I get is 4 groups of circuits. What is the place of the silent neurons here? I mentioned before the Nobel Prize of the silent neuron. Where are silent neurons? In each of these groups, there is a couple of silent neurons. So it shows you that a silent neuron can complete structure of, say, a 7 category group of circles, sorry. But in each of these are the categories that I showed you before, and you cannot go beyond without repeating what you had before. But memory we know that memory can be considered more far-reaching than 7. We know that people remember whole books, people remember whole music pieces, even a complete symphony. People can whistle a Beethoven piano concerto completely. So it's a lot of memory. So how can this happen if what I just showed you is that memory seems to stop after a certain small number of circuits. So my idea was to build trees of I call it meta-periodic interactions, but it's groups or trees of primal size neurons. Why is this so important? Why even exciting? Take a circuit of 2 neurons and connect it to a circuit of 3 neurons. Both are primal size, right? If you compute how long a cycle will go in such a structure, you end up after 6 steps to come back to the beginning of a cycle. If you go if you examine another constructions of one primal size and another one is not primal, although here you have more neurons, the cycle is only 4 steps. Why is it better here? Because memory wants to include more information, a lot more information. If you, let me see, just a minute. Okay, yeah. So some people like to see time sequences of firing. So let's look at the first 2 neurons, 1, 2, 1, 2, 1, 2, 1. And you go to the 3 neuron circuit and you get 1, 2, 3, 1, 2, 3, 1. Okay, what happened here? After the first step, you went 6th step and you start all over, okay? So it leaves something complete and new for a length of 7 steps, 6 steps. The 7th is starts a repetition. Let's look at another situation. A tree of 3 primal size circuits, okay? And I do the calculation here. I'm not getting you into this, but if you count what the total cycle here is, it's a 30-step cycle to come back to the original step. If in the non-primal case, here also 2, 3, but instead of 5, I have a circuit of 4. The difference is very substantial. Instead of three-step cycle, I get just a two-step cycle. So what's so bad? No, I want to be able to store large pieces, long pieces, without repetition. Okay, a music piece, a nice music piece, has no repetition. There's something maybe close here and there, but no exact repetition, and a good story doesn't repeat itself. So you want to go primal, and you will see that here I have one circuit, a circuit of one, and then I have a circuit of two, and I have a tree now of 1, 2, and 3, which are prime numbers, primal size circuits connected. And I go down all the way to 10 circuits, primal size with connections, but there's no repetition. And I go up to 200 million, 223 million steps without repetition. Now that's, it's not a lot of demand from the cortical brain, right? Just 10 steps, 10 circuitry, not too large, and it stores a lot of information without repetition. Okay, so that's my concept of how does the brain, having just small circuits, store a lot of information and memory without repetition, if it wants to. All right, that what I wanted to say about the connectivity. The second aspect is firing rate linguistics, which I call the second driver of the mind, because the mind, neurons fire, and it's firing. The difference between the firing of the different neurons, which produces information and activity and so forth. Now, firing rate is described by dynamic equations, which we know from control theory and mathematics in general, by cobweb diagrams. I'll mention, if you haven't seen it before, then I'll say something about it, and by time sequences, and by global attractors, which are a term used for describing modes of firing rates. The firing rate mode can be chaotic, can be oscillatory, can be multiplex, can be fixed point. There are several of them, and let's see. The first, say, mathematical equation for describing neural firing was suggested by Lapik in 1907, and he followed where the Spanish who discovered neurons by just a few years, and it was followed. The peak was followed 60 years later by Hodgkin and Huxley, who really loaded the science with very elaborate equations of motion, and they received the Nobel Prize. And then some other mathematicians reduced Hodgkin and Huxley and said, well, you can do with smaller equations, with less mathematics, and they were Wilson and Cowan, Hubbard, and then Gerstner, and their model was like this. And actually, Wilson and Cowan said, well, you can give up the interval and still get a very good representation of firing dynamics. I took that and changed it into discrete time model because using a computer, of course, it's easier to work with discrete time dynamics. And I also made a distinction between time periods, living time periods of humans, looking at the pre-critical period, which is actually prenatal period, and critical period, which is ages 0 to 2 or 3, and then maturity and rigidity period. Rigidity refers to older people. So the maturity period is the longest, and it is shown here. What is shown is really the neural synaptic excitation and inhibition stages. Excitation being an upward motion, and inhibition being a downward motion. And the period I was concerned with is represented by this model here. I'm not being too specific about things, but it was very easy to describe evolution of firing modes by cobweb diagram. Cobweb diagram were invented by Koenig, a French mathematician, in 1884. I used those to write a paper of explaining how firing rates can change. And of course, if you have a changing firing rate, you can do different things. The brain can do different things. So using cobweb diagrams, I created 12 different modes of firing. And I presented them by cobweb diagrams. And like the first here is a chaotic mode. The second is largely oscillatory. The third is multiplex. The fourth is fixed oscillation, and so on. And they were the first 6. And then another 6 fixed point, bimodal fixed point, different names, but they all have their functions. And some people prefer looking at time sequences of firing rates. So here you have, remember I started with the chaotic one, here it is, that's a chaotic sequence, and after learning, I also mentioned the learning stage and then the retrieval stage. So this is chaotic, then there is a pseudo oscillatory, then there's an exact oscillatory. So these are three modes I took from the first group, and then I took two modes from the second group. This one is a fixed point, which is a constant firing rate, and then silent, because we saw that silent neurons do have significance. Now here is interesting from a different viewpoint. Indeed, it's a cobweb diagram, but it describes what happens if you take the same neurons, same type of neurons, same parameters, everything, but a different number of neurons, and how a different number of neurons in the circuit completely change the behavior of the circuit. For instance, two neurons here produce an oscillatory sequence, an oscillatory mode of firing rate. 5 neurons, largely oscillatory, 7 neurons fluctuating, 11 neurons chaotic, and they all neurons of the same type. It's just by changing the size of the circuit completely changes the firing mode. Let me say something about memory. Suppose you have a circuit of 3 neurons and they fire. And in this case, it's just by choosing the parameters of the circuits, of the neurons in the circuit, we change the local behavior of the circuit. So here, the original behavior was chaotic. And 1 neuron went to sleep or died or something. So you're down to 2 neurons, okay? So you have an oscillatory sequence. Then one of the 2 neurons also goes to sleep. And you remain with 1 neuron who is a fixed point dynamics, firing rate. And that's the 3rd one. And then that one also goes to sleep. So you stay without memory. It's 0 from there on for a long time. And all of a sudden, one of the neurons wakes up again. And it's the last one who went to sleep, now gets up, is awakened by some external stimulation. So you have the fixed point section part, and then the other neuron wakes up, and you get oscillation, and the 3rd neuron wakes up, and you get back the entire chaotic mode. Okay, so that's a complete memory restoration. Okay, but we know memory is not always perfect. You don't always remember everything. So that's just a small example here, that after the 3, the 2, the 1, just one of the remaining 2 joined, and you stay with this mode. So it's partial memory, and it makes sense that you don't always remember the complete description of what happened the time before when you experience something. You remember part of it. So that's an explanation of partial memory. Now, I leave most of the mathematics behind, and I want to talk about people. Consider a person walking on a tile floor, and you can see the angle of sight, and there's isochades, so you know, jumping from one tile to the next. There's a change in the retina, and at some point he or she may stumble or even fall and stay without motion. That's what the retina, how it sees the tile, and that's the expansion of the tile on the photoreceptors of the retina. Looks something like this. I'll skip the mathematical representation here and get to my the side of the story. It was when I visited, I don't remember exactly the place in America, and I watched television, and some doctor who had Parkinson told this story. And I looked at it, and I all of a sudden said, look, there's something that can be helped, can be done to help people like that. I came back and started thinking, and I had an idea to build a box which stores a small computer and is connected to eyeglasses to say, a portable display, something you can put on the eyes, and earphones. And this is a person who happens to be me with the device on. And what he sees is tiled, virtual tiled floor with his own steps over on the tiles, seen on the tiles. Something about control. There's open loop control, which you see here. And open loop control has been used and has been recognized as something that can help, but can also be very dangerous. Because if there is a diversion, if there is a disturbance, there's no way to correct it. And that's how airplanes fly into mountains and lightweight airplanes of the old past. People may bump into things, etc. This is all open control. But I said, okay, let me also check this against the open loop control system. Open loop control systems are generally stable because correction, diversion, whatever here is corrected. Diversion here, disturbance from the wind, from the shape of the ground, etc., can be corrected, can be repaired, and this is a stable system. And I built the two versions of the device. Again, mathematics for other time. And I tested one person, which I will show you the experience there. And then together with a colleague in Rambam Hospital, who treats people with Parkinson. We had 14 patients. Of course, we measured and recorded everything and kept information. I'll show you the averages. Percentage improvement in open loop. With open loop control, the walking speed improved by 11%, the stride length improved by 13%. Percentage improvement in closed loop, using the closed loop system, walking speed improved 22, 23, and stride length 19%. About twice, almost in both cases, twice as good as the open loop system. Another thing I wanted to check, and those were preliminary testing that I did, was which is better. Martin, the one who first tried to help Parkinson's patients by drawing lines on the floor. And he published his results in 1967. And I asked myself, okay, let's see how good these are. As compared to glide symmetric tiles. Tiles are usually glide symmetric, and for a good reason. The person walking has a glide symmetric motion, okay? It's one step, then the next step goes over the first and so on. So glide symmetry is a natural construction. Here, and my these tests were on multiple sclerosis patients, which were my next group of patients. And I compared the transverse lines. Improvement percentage was something like say between 20% to between lowest one was 3% improvement to 20% improvement. The stride length improvement was about the same change, same improvement. When I tried the checkerboard tiles, and that was virtual construction, the improvement was transverse lines on average improved the walking speed by 7 to 8%, and the walking speed by also about 7% in stride length. Average improvement in checkerboard tiles was 13%, and in walking speed 21%. So checkerboard tiles were much better. Let me show you some of the early experiments. Here is a woman who was 50 years old with Parkinson. She didn't take her medicine the night before. And I took her from her doctor's office for testing my initial device. The device was, you see, she had to be pushed from behind. The device was very preliminary. There was a large computer on the side, wires connecting to a pilot's helmet, which would be put on her, and we would examine her walking after with the device. Here, she has a device on. The computer is here on the side. The helmet is here with the, the glasses. And she starts walking. On her own, we couldn't believe our eyes. She was walking perfectly, no medication. So that was extremely encouraging. About 3 years later, I had a much better device, not connected to a computer on the side. The computer was embedded, connected to the belt, and I pulled the patient out of bed, and so forgive the pajamas and everything. And you see the Parkinson there, and the nurse has to support him, and that was his performance, walking without the device. And no, sorry. Okay, now I put the device, the new device on him. Just a couple of minutes ago after, and there it is. So walking is almost perfect. The nurse stays behind. Again, a complete excitement on our part. I was invited to the University of Cincinnati to give a talk about this device, what I came up with. It began to be published, and I said, okay, I'll give a talk, but please have a patient ready after my talk so I can demonstrate what it does. So sure, I gave the talk, and everybody came out and followed our demonstration here. And this was a Parkinson patient. You see, they got stuck at the line. They have a problem with what they see and how it helps or disturbs their walking. Again, the same thing, stuck and move. And okay, now I put the device of that time on, and that was the doctor who invited me, and you see the difference with the device. Much more confident. I came back to Cincinnati in a few years later. They invited me for a sabbatical, so I spent time with the doctors there. And again, the device became much more suitable, small, easy to use. Here is a patient. You see, that's Parkinson. Very difficult to walk, to make a turn. So without the device, he did his best, but again, not easy to do. And putting the device on. And again, I want to show you the turn that he makes. It's much easier now. Okay, what else? Okay, I came back to Israel after that sabbatical, and I worked with multiple sclerosis patients. And here's a guy. The MS patients are younger. You see a guy here. You see the walk is not consistent, not here with the device. It's not perfect, but at least it's a straight walk. Okay, skip. Then I tested kids with CP, cerebral palsy. Without the device. Another one. Ah, sorry, I should have shown you the one with the device. Sorry. I need to see it. Okay, you see the wire there, so he's with the device. The walk is more confident and I think this one is with the device. It's more confident. I have the different patients' numerical results, what we measured and everything. Okay, here you have we had 10 patients with CP. The improvement is shown here. You see they're all improved. Walking speed and stride length. One is not improved, but all the others two of them here did not improve. 1, 2, 3. But the others had a very significant improvement, up to 110% and 13, 22%, 23%, etc., 47% improvement in walking speed and stride length. And that was with a visual device. That's the auditory device. I didn't mention the auditory device, did I? But the auditory device was quite effective as well. And you see that the improvement percentage was quite high. To be sure about the result, I approached a friend who was a school principal, and she allowed me to do experiments on healthy kids of the same age. And with them, I saw, in fact, deterioration. They were sort of taken down by the device. So you see that, in fact, how difficult it was for the CP patients to use the device, but how it helped them. And patients who didn't need it really performed worse than with it. Sorry, than without it. So that's about the end. Thank you.